Thank you.
Bye.
Bye.
Hi, Kate.
Hey, how are you?
Good. How are you?
Excellent. Thank you so much for joining us tonight. Thank you to everyone.
Pleasure.
It's really great. I'm so happy and pleased to see so many people joining us today. Larry is with us already, and I'm excited to have another one of our series that will be helpful to humanitarian technologies and to all the things we're trying to do to improve opportunities for people who have all kinds of needs, and also to help people to understand what we can do as IEEE members to make a difference in the world. I'd like to introduce Larry Nelson, who is with us now from the National Grid, and he's going to spend a bit of time helping us to understand how his work helps improve opportunities for people who are having disabling conditions, who may be experiencing power outages, how they manage to figure out where the outages are, and how they do a significant amount of work to make sure people are back online as quickly as possible. Larry, please take this opportunity to help us understand your work.
All right. So can everybody hear me? We're testing out
Yes.
audio here.
Yes.
All
I
right.
can hear you.
Okay. All right. Let's see if we can share my screen and we'll throw up some slides. Let's see. Share screen. Share. All right. Oop, nope, I don't want that.
Different screen.
There we go.
Excellent.
And I think this thing here, if I just hit this, or do I hit this one? Hide thumbnail video. There. Okay. And slideshow. All right. I think you can see this. Okay. There. All right. Everybody can see the screen now?
Yes.
I hope. Yeah.
Yes,
Okay.
I can see the
Good.
screen. Yeah.
All right. So it looks like we are 3 minutes after, so I think we're good to get going. So my name is Larry Nelson. I am an IEEE senior member. I have been within IEEE since I was around 4 or 5 years old. I started going to meetings with my dad, and I've been in it ever since. When I went through college, I joined as a student member, and I've worked my way up through. So I've always had my hands in IEEE. But my career brought me to the utility. So I work at National Grid as a principal protection engineer. And what that means is I deal with the devices that detect and have to deal with things going wrong on the electric network. So I program devices called relays, and their purpose is to sense something going wrong on the network and isolate the problem so that way nothing gets damaged. So that's why I am called a protection engineer. I am protecting the electrical network. And in a sense, when I turn off that electrical network that's damaged, I'm also protecting the public from being injured by that electrical problem. So that's what my day job is at the utility. But my what they call storm roll is when the electric system is in essence under attack by major storms and events, maybe an ice storm, maybe a hurricane, things like that. My role is to be a what they call damage assessor. and I have to go out into the field and find things that are broken and describe what is broken, so that way we get the right utility crews on site to repair it. So I've been doing that job for over 16 years now, and I have seen many different types of damages, and I've seen how the restoration of our system happens from my company's perspective. So I'm going to use that as my knowledge base to help share all this with you guys. All right, now let's go to the next slide. So just a little bit about this presentation. Much of the stuff I'm going to talk about, I'll try to keep it generic and will apply to any utility, no matter where you are from. But my personal experience is based on one company being National Grid's methodologies. A lot of the photos and diagrams I have, they're all from just general Googling and checking on the web. So it's nothing specific to mine, it's just general examples. But when I get into some photos, those are things I saw in person when doing my storms and damage patrolling, to give you guys real world examples of what has happened out there. And then some of the stuff that I am going to show that is specific to National Grid is just from the public website, so anyone can go and look at the stuff. And if anyone wanted to look for an equivalent, I'm sure there's similar things from the utilities each of you are a customer of. All right, so to get started, let's talk about how the electric system is connected. And I'm going to talk about this a little deep, but I'll try to keep it high level. And I'm going to use my arrow to point a lot. So this is an electrical diagram of a typical substation, and it's trying to show stuff inside of a substation and stuff that goes all the way out to your house. And there's a couple of key things I want to point out to people here. One is, so these little symbols here, these are transformers. This is the high voltage transmission lines that run, that you hear about in the right-of-ways that bring the power from the generators to our towns. You might have one of these stations in a town or in a big neighborhood. And as you can see, we have more than one transformer. The reason? Redundancy. We don't like losing power. So we try to make things redundant so that there are less likely a chance of something losing power. Now, the other thing we do is we break up areas into what they call feeders. So there are multiple connections coming out of a single substation going out to different parts of a town. And once, and this is an example, once one of those feeders goes out into the streets and all that, it's broken up into multiple paths. So, and each one of these paths, this little symbol here, this little squiggly line that we'll see, these are fuses. These are no different, other than the amount of power they can handle. They're no different than a fuse that would be in your house or in one of your, like in your car, the little fuses that protect your car. It's just these can handle way more power. But the idea being, if something goes wrong in this little section, maybe these are, each one of these is a customer, then this fuse will turn off everybody that is connected to it. So these customers will all lose power when this one device turns off. And same thing down here. You know, this one fuse will turn off this one customer, but this one fuse will turn off these three customers and this one customer, because all the power has to flow down this path. And this is just to kind of give you guys a representation that depending on what item turns off really decides how many customers turn off. And then we have a little device like this called a recloser that you'll see up on a pole sometimes. And its purpose is to turn off when something goes wrong down here, but then to try to automatically turn back on and bring people's power back. And you'll know if you have a recloser operate in your area, because your power will go out for about 5 seconds and then it'll come right back. That's because one of these devices saw the problem went away, and the power came right back. So this, and then this, what you see here, this is replicated on every single one of these feeders, something similar. And what you see here in this substation, one utility might have 300-400 of these substations just like this. And that's how we power an entire state. So as you can see, there's many different points here that things can turn off. And depending on which ones turn off decides how many customers lose power. Now, the thing I wanted to point out on this about how a utility is connected is not only do you have this scenario here where everything comes off of this one point and feeds these customers, but they have these little thing here is called ties. And what that does is and that's what we're seeing right here, is if there's a tie, I can maybe feed all of these customers from another substation or maybe from another feeder. So like what's shown here is I have this big power source and I have 2 feeders, but either feeder can feed all the customers. So I can open either one of these and the customers still stay powered. So it's all about redundancy. We're trying to keep everybody on as long as possible. And if something goes wrong, we want to have another way to get them power. Now, we were just talking a little bit about all those different feeders. To help picture in your head, what does that mean that I'm on a feeder? Well, this is just a neighborhood. And on this neighborhood, each one of these colors is a different feeder. So as you can see, one street might be on one feeder, but the houses right next door, they're on a different color. That means they're fed from a totally different path. So if something is broken here, it doesn't mean the people over here are broken. So you might think, oh, well, everybody in my town is fed from one station. Well, that's true, but different streets are fed from different parts of the station. So it helps to know, why do I not have power and my neighbor does? Well, it could be something as simple as this. You're fed off of this one and this one's broken, but your neighbor's fed off of this one and this one is fine. So it really helps to illustrate why you are broken up into sections. Now, what makes things go wrong? Why would you lose power in the first place? Now, to help understand that, it's good to understand what's on the poles that are outside in front of your house. And this is 2 different pictures of the exact same thing. We're looking at a telephone pole. And on that telephone pole, there are multiple things. Starting at the top, that's where the distribution power is. So things up here, these are normally either 4,000, 12,000, 13,000, maybe even up to 23,000 volts that are riding on the top of the telephone pole. And that's this ABC phase that we see over here at number 3. Sometimes above the power is what they call a static wire, and that's just protecting it from lightning. Not all distribution poles have it, but if they do, it'll be this single wire way on the top. Now, once you get below these 3 wires, you end up with and they're sitting right what they call on the cross arm, and that's how you'll see them most of the times in our neighborhoods. But sometimes you can see them vertically like this, where they're ABC phase going up and down. But this is not what's directly feeding your house. What this feeds is these cans that you see on your street, and these cans are the transformers that are the step downs. And what they're doing is they're taking 13,000 volts and they're turning it into 120 volts or 240 volts to go into your house. And each one of these little transformers has this little device on it. And this little device is called a cutout. And you'll see them, they look just like this in the picture. And that cutout is just another fuse. So it's one more spot that can turn off if something is wrong. Now, so right here, this primary, that's the high side of the fuse at number 6. And then over here at number 10 and number 9, that's the low side of the fuse. Now, or rather low side of the transformer. Now that transformer might not feed just one house. It might feed 6 or 7 houses right next to each other. So if this transformer blows up, one customer might lose power, or maybe 7 or 8 customers might lose power. Depends on how it's connected in your neighborhood. And it's based on how much power each house is asking for and how big this transformer is. Now, the other thing that can happen is people will see wires down on the pole and they'll think it's that's why they lost power. So they're trying to get the utility out there. Well, if those wires on the ground are these wires down here on the bottom in the what they call the communication space, and it's a communication wire, or maybe it's a some fiber optic or something. And normally those wires are done by companies like AT&T, Comcast, Verizon. They will own these wires. If those wires are down, that is not why you have lost power. These wires can be cut up to shreds. A tree can be leaning on them, any of that. It's not why you've lost power. And a lot of times what will happen is when somebody will say, oh, the power line's down in my street, I'll be the person that will drive over there, go and inspect it, see this wire sitting there on the ground and say, nope, that's not why you've lost power. And you'll see the utility person drive away. And it's not because they're ignoring, it's because they know that's not where the problem is. And that's for the communications company to repair, but it won't stop you from having your lights turn on. So now that we got a little bit of education of what's out there and how does it generally work, now let's talk about when things go wrong. When the power goes out, what happens on the electric system is a few things. One, the voltage will drop. Now, if the voltage drops, devices won't turn on. But that's one characteristic that we can use to figure out what's going wrong. The next thing that normally happens when the power goes out, because something is fallen or broken or that, is the current at the location will increase. So that's something we can sense and detect. So we can see that the voltage is going down and we can see that the current is going up. Now we know the power is completely out when we also check our meter. So the meters that are on the side of your house, if it's one of those old induction disc meters, it'll stop spinning and you can go out and check the meter and see it's not spinning anymore. If the meter is one of the newer digital meters, it won't turn on. You won't see any LEDs, or you won't see the LCD display showing anything. It'll just be a blank. So that's a good sign you've lost power, but that's also how the utility figures out you lost power. Is we sometimes will go up and walk over to your house and look at that meter and see, yep, it's not spinning, something's not right. But here's an important thing. Just because your meter isn't spinning doesn't mean us at the utility know that your meter isn't spinning. Most meters do not have communication, and they do not talk back to what we call the control center that's telling us where the outages are. So there's no real way today under 80-90% of the meters that are in service for us to know. Now we are deploying new meters. Sometimes they're called smart meters. Some of the smart meters have communications back, and we will eventually be able to tell that a customer doesn't have power. But under most circumstances, just because your meter is not spinning, we don't know you don't have power. Even though we are reading that meter to charge you your monthly electric rate. And the reason that we don't know that you lost power, but yet we still are able to talk to it for a bill, is we talk to it by either driving by in a van and we ping it, or sometimes it communicates all the way back, but it only gets pinged one time a month to a certain department. And that one time a month is not enough for us to tell you that you don't have power. The way that we do know that you do not have power is devices that detect the problem and open up, such as those reclosers we were talking about, those fuses, the breakers that are at stations. Some of those devices have what we call telemetry, which means that they have a radio or some kind of comms device, and that will tell our control centers that the device is open. And when it tells us that, we know immediately how many customers were below that device and how many customers should be without power as a result of that. So we use that to get an estimate of how many customers are without power. The downside is we know they're without power and we know that something went wrong down there, but we don't know where it went wrong. We don't know what broke. We don't know why it broke. We don't know if it fixed itself. We just know that it's open and people are disconnected. Now, here's some examples of what disconnected might look like. Now, this particular photo set was taken, let me think, this one was in Worcester County of Massachusetts, and it was during a windstorm came through. And when this storm came through, it just knocked down trees everywhere. And as you can see here, some examples right here, I can see some gutter work, some secondary wires on the ground. I can see the primary, which is what should be up at this top of the pole, is missing all here. So I know this is some major damage. I can see giant trees are in the area. This is going to take days to repair. This is not a quick fix. Over here in this picture, I see all these giant wires hanging on the ground. These were the 3 wires, because I can see way back here that there should have been 3 wires. I see no wires up here, so that all these wires dangling over here, these are all the main power that feeds this. If those primary aren't there, it doesn't matter that the transformer is okay and everything down below, and the wires are connected to your house. Until they can repair all this, you're not going to get power back, and that's, again, multi-day repair, multi-hour repair. And even this, I see this telephone pole is leaning. They're probably going to have to dig this up and replace it. Now, from a safety perspective, the only thing I'd say is this wire is most likely dead, but there's no guarantee it's dead. This person is in a very dangerous place. When I was driving down here and took this photo, I yelled at the guy not to be in this area, because somebody, these utility guys over here might have been trying to turn on something. They may not have expected it or looked at the damage down this far. This could have been energized and killed the guy within a mere minute. So when you see wires down like this, even if it's dead, don't physically get anywhere near close to these wires. They're very dangerous. And we are taught not to get out of the cars, even to go look at this damage. Now, this is a different storm. This one happened down in the coastline of in the Brighton Point area. So this was down in the Cape area, and it was a another big windstorm that came through. This telephone pole snapped in half. Now here, all the customers have power, but we're going to be turning them off probably in a day when the crew gets out here to repair this. So you might have had power through the storm, but you're about to lose power for a day. And we're not going to go necessarily door to door to tell you you're losing power. So you might just find a day after the event happened, you lose power and it doesn't come back. It's because we might be repairing something like this. And this I wanted to point out because this here is just a single person house. Everybody in the area has power. Even this customer right now, even though his wire is on the ground and it's touching this car, he has power to this house. We're going to send an electrical crew here to cut this wire to de-energize it so that it's safe for the road. But this customer is going to be without power now for a while because he's going to have to repair all of this, which he owns. This is an example of, very low priority after we've cut it clear. So we're going to intentionally de-energize this customer, but we're then going to go off and repair things like this that impact multiple customers. We'll come back to this when the customer can repair it. So he might be without power for multiple days, getting inspections, sign off, and you have to be prepared for these kind of events to happen.
Can I interrupt
Yep.
for a moment and ask a question? So
Yep.
when you say the customer has to make the repair, how would the customer go about making the repair?
Oh, yep. So in this particular case, where the ownership changes from a utility to the owner of the house is at the top of the weatherhead. So this piece here is called the weatherhead, and it's the part that goes from your meter and goes to the top of your house. That portion right there is owned by the owner of the house, and that portion would be needed to be repaired by an electrician. So the customer in this case would go hire an electrician. The electrician would then have it inspected by the town inspector, get a sign off that the installation was done correctly, just like as if you did any electrical work at your house. And then the town inspector and the electrician would call National Grid and say, I've repaired it, please come and reconnect this customer. And then the utility would come out and reconnect the customer.
And do
And because,
customers get informed that this is what the procedure is and that's what's expected of them?
yes, normally when I come across something like this, when I find the damage, if the customer is not already aware that it is their responsibility, in my case, our utility gives us door tags that we can hang that explain the ownership points on your electrical house, and the procedure that you need to do. A lot of utilities also have it posted on their website. But and anyone that comes to do the repairs, it would be able to explain it to that customer. But also, if that customer called back and said, hey, a utility crew came here, but they just cut the wire and left, what happened? Even a customer service rep would have the information, because it would be updated in our systems that there is customer damage that needs to be repaired by the customer. So there's multiple ways, depending on how the person runs into finding out that it was their responsibility. They can contact, the utility directly. There's normally physical information handed to them if, they are home when the person comes. But yeah, there's multiple ways they would find out that that's their responsibility.
And is this the matter of maintenance, that the homeowner was not maintaining their
Oh,
system?
no, nope, that's just, I mean, that tree branch right there fell down and ripped it off.
Got it.
So this would be a matter of, how would you pay for, like, in terms of pay? I think you can file it as a home insurance claim. It'd be no different than that tree branch went through the guy's roof. It's just, in this case, it went through their part of their electrical service. So I'm sure you could file through your insurance company. But yeah, I mean, that's the catch, is you got to know what you own. And the example would be, let's say you go and you want to upgrade your service at your house. You have a 100 amp service and you want a 200 amp service. You would hire an electrician to replace this wire with a thicker wire that could handle the higher power. That would be a normal expense of a regular upgrade for a customer.
And if you were a disabled person living there, is there any special help that you could get to manage the repairs or understanding what you need to do?
And no, I mean, so that level of explanation would be identical no matter what kind of customer it is. Disabled, regular. I mean, customer service. If there was misunderstandings, I'm sure customer service would be able to provide additional detail if you needed it in writing or things like that. But even the town would be able to provide that information, because the town inspectors in that would be responsible for this aspect too, right? The utility is not allowed to connect it unless the town signs off on it. So I would think the other resource besides the utility would be the town inspector's offices, for somebody that wanted to be prepared for this, not deal with it as it's happening.
Thank you.
Hey, Larry.
Yeah.
Quick question. Out of curiosity, what's the cost of all these repairs versus burying the lines? The cost of burying the lines.
So the repair of something like this is normally a few $100. Because and it depends on, if you've got a decent electrician, he's going to charge you an hour, and he's probably going to just put this back up with a couple of screws and that, and then he'll charge you for an hour of dealing with the inspector and stuff like that. So it's probably a few $100. Maybe the cost of the PVC pipe for repair too, depending on the level of damage. The reconnect from National Grid, that costs nothing, or from any other utility, that's you don't pay for that. And you don't pay for the inspector to come out and check, because that's part of the town services. So I mean, this cost is probably a few $100. If you chose to say, I want an underground so this never happens again, that can be a couple $1,000s, I've heard. And it's because you have to pay to dig the trench, and you have to pay to buy the cable that goes in the trench. Because you will own that all the way to the telephone pole, because you'll probably want to run it underground all the way to the pole. So you would own all of that. Once it hits the pole, it's then the utility's problem, but everything underground you own.
Okay.
Okay. So now we can get into the what you as a customer need to do. So all the stuff I showed you is what we know as the utility by ourselves. But you as the customer, you telling us that you lost power is a very large part of this whole process. If you don't tell us you lost power, we may not know you lost power. And the scenario is in that picture we were looking at here, if you didn't call us and told us your wire's on the ground, we would have no idea other than pure luck that we stumbled across you. If this had ripped off and you lost power and all your neighbors had power, no neighbor's going to call for you to tell us that you lost power. So if you don't call, we don't know. So it's always important, no matter whether you think the whole neighborhood's out, everybody should always call. And it's because the more people that call, it becomes that much easier for us to guess where's the broken part, right? So maybe this fuse has no telemetrics. There's no way for a computer to know by itself that this fused open. But if I know this customer called, I go, well, oh, it must be this fuse. But if I know that customer called and this customer called, he didn't call, but I got 3 out of 4 customers, you know what? It's most likely this, especially if I know all these customers are okay. So it helps us find the problem and it helps us repair it faster, the more customers that call. So very important. Tell us you lost power. You can tell us by phoning us. You can tell us by going on the website and reporting. You can, and see right here, you can say, hey, I got no power. Or, you know what? Some lights are doing weird things in my house. Or they keep flickering and I have no idea why. Telling us that tells us what kind of problem it is and where it is. So it's always important to tell us. Now, with that information, we can
Larry,
tell you, yep.
can you tell us what flickering means?
Flickering would be your lights keep turning on and off. So for example, your LED lights in your living room keep blinking at you and they're blinking really fast or they're blinking slowly. Maybe they're on for 2-3 minutes and then they turn off and then turn right back on. And then a couple minutes later, they turn off and then turn right back on. That's not a normal behavior, but it tells us maybe there's a tree branch on the wire outside your house.
Aha. So so it helps you troubleshoot what the problem is, and you think it might be an intermittent problem or a problem.
Exactly.
Okay, great.
Exactly. Whereas if you tell us your lights are completely out, well, that means we probably blew a fuse somewhere or something got ripped off, right? So that's a different level of problem. And depending on what the problem is, we might send a different kind of crew. So it's all about, what's the fastest way to get you your power back working normal is to know the most about what your symptoms are. It's just like a doctor. The more you know of the symptoms, the quicker you can get the correct diagnosis and get the fix. Now, what I'm showing here is that if enough customers tell us what's going on, we can then tell other customers based on what we've learned. So here's an example of a map that is publicly available that you can see where the outages are in your area. Now, in this case here, this is showing a map showing, hey, there's 2 outages way over here in this town. And I clicked on that little number 2 and it showed me, hey, I know there's 2 things going on. And I'm expecting that those 2 things are affecting 11 customers. Now, that's based on the data I have. If more customers call in, well, maybe I got 3 things wrong, or maybe the 2 things that are wrong are affecting a lot more customers. But based on the information I have at that moment, this is what I can tell. And systems like this update about every 15 minutes. And with that information, you can go and look at your house right down to the street and you can get information about the outage that is impacting you. You go, hey, I live on this Blackstone street and I have no power. What's going on? Well, I can see, hey, you know what? There's 7 other customers that have the same problem as me. And they're right in this area. And I can see, yeah, that sounds about right. I lost power somewhere around 140. Well, hey, look at that. Based on now what the utility knows about your problem, we've assigned somebody. So there's a crew on their way to repair it, or maybe they're actively working on it right this minute. And we can also tell you, you know what, based on what we think we have to fix because of what you've told us, we think you'll have your power back by 8 o'clock. So now you can start planning around this. You can decide, do I have, the emergency medical stuff that I need if if I'm somebody with this disability that, that's important to know. So it really helps you plan by sharing information with us. We can share information with you.
So the community might be able to have a shelter prepared for people in their community that have disabling conditions. And when they are alerted that this kind of outage is in their
Exactly.
geography, in their region, that then they might even be able to reach out to their local people who live in these regions and arrange.
Exactly.
Okay.
And
That's
this,
a very cool thing. Yes, that's very cool.
and this is also useful of, hey, you know what? I see, yeah, I'm without power. I know my neighbor a few houses down has got an oxygen generator. And I go, geez, they're going to be out till 8 o'clock. But you know what? The house next to us on the other side has power. Maybe I should go talk to the neighbors. This, gives you a little bit of insight too to, help out your neighborhood besides, the services that are available from the utility in city and towns. It's really also can help neighbors helping neighbors.
That's right. Very cool. I mean, it's possible that we could figure out a way to make these kinds of plans where we can estimate what neighbors have resources or what larger centers have resources and then make recommendations, for example, right?
Oh yeah. Yep. Now, if you've lost power, how do we decide who gets it back first, right? So that if something goes wrong, I can only help so many people so fast because I've only got so many guys that can climb poles. Now, if there's only 2 things wrong and I've got 10 crews, that's great. I've got enough people to throw at the problem. But if I've got 10,000 things wrong and I've got only 100 crews that I've pulled in from all the states and surrounding neighbors, I'm still in trouble, which means you're going to take time to repair. So how the utilities normally prioritize is number 1, public safety. Now, the example that would be a public safety hazard would be there is a wire down and it is arcing and sparking and catching the lawn on fire, or it's touching, or a fire truck is calling the utility saying, I'm at this location and there's a wire arcing on a car and there's a guy inside the car. You need to come fix this now. That's what they consider a public safety hazard. That's what we would consider a 911 call, highest priority. People go, and that's what we're fixing now. Second highest priority, safety facilities, public health facilities, and critical customers. Public health, that's your hospitals, that's your critical power lines to, the community center, the clinics, things that have to do with keeping other aspects safe. The police station, the fire station need power. Those are critical. And critical customers can also represent some aspects of individual customers, but most times it's more about that facility that is helping multiple people. The next highest priority is the major feeders. So that's when we were looking back at that map. When we say major feeder, if this breaker is open, all of these customers out. That is more important than fixing this fuse that only has this one customer. And it's more important than fixing this recloser, which has all these customers down here. So we prioritize based on what's the biggest bang for the buck. If I'm going to spend an hour fixing something, what can I do to get the most customers online after I've taken care of the highest critical customers? So I fix my highest critical customers. Then I try to get the most customers I can fixed. So I'm going to spend resources fixing the major feeders. Then I'm going to go down to the next level and say, okay, where do I only have like 50 customers out or 100 customers out versus the 7,000 customers out, and try to fix those little problems piece by piece. And then our last thing is, after we've fixed all those, we're going to go to that guy that has the one wire sitting on his house and has been ripped off of his house. Because if I spend an hour fixing that, I've only fixed one customer. Whereas if I spent an hour with this, I might have fixed 50 customers, or I might have fixed 7,000 customers. And chances are, there is a bunch of individual customers inside of each of these problems. So if I don't fix the feeder, it doesn't matter if I fix the customer's house wire, because I still got to fix the feeder to bring his whole house back alive. So that's kind of why we prioritize it this way. But there is a subset of, what can we do to prioritize maybe which neighborhood do I go first? Which feeder do I go first? Which customers do I go to first? And that's where this comes in. Critical customers. Now, that sometimes can fall under that second category of critical customers, but it definitely changes how we prioritize 3 through 5. And sometimes it can fall into category 2. But this is a form provided by the utility that says, if you have any of these conditions, tell us, because you are considered a critical customer to us. Now, as you can see here, talking about heart rate monitors, oxygen pumps and concentrators, suction machines and pumps, medical pumps, dialysis machines, ventilators, all these things are critical things that if the power goes off, the person might die. And we want to know that if that's true, that we really want to get your power back first. So if you have any of these, we want you to fill this out. We want you to tell us so that we take extra care with you. For example, when this happens, if there was a critical customer in this, our customer service is probably calling that customer and saying, we fixed the 7 customers we think. You did get power back, critical customer, right? And we don't want to just assume that customer got power back. We want to be very certain he got it back because of how critical it is for their safety. Okay. And what you do if you are a critical customer, most utilities have a website or something, or you can call your utility, but they want you to tell them, in this case, National Grid has a form and they want it mailed to this location, or you call and tell them you're filling out this form. But that's the kind of stuff that if we have on record, we will keep track of. And it's something that needs to normally be updated annually. It's not you do it once and you're good for forever. We want to know you keep needing it. So we're going to keep checking on you, say, do you still need that? Do you still need that life device? To keep our records as accurate as possible. Because if you don't need it anymore and there's somebody else that does, we want to make sure the person that really needs it is being prioritized, not people that said they needed it, but then no longer need it. And then the other thing that they love to point out is, important thing, a power outage can happen. So, even being on this life-sustaining equipment list, it doesn't necessarily mean you will get the power back immediately. We'll do our best for you and we'll try to tell you even more information than we tell the average person. But you need to be prepared that you may be without power with some time. And as they say, always dial 911 if you're having a medical problem. Don't tell us that your medical problem is you have no power. If it's that critical for you, call 911 because they will get you the life-sustaining supplies, even if we can't get you the power first.
So Larry, I wanted to ask you about the CPAP. I think you mentioned on your slide, one of the items listed. How does yes. So that, is that a cause for being on this life-sustaining equipment list?
Oh, let's see, CPAP.
Apnea monitor, this thing here. And the intermittent positive pressure respirator. That's what,
oh yeah.
yeah.
Yeah, I guess it qualifies you. Yeah. I know they review this list on a semi-regular basis.
Yeah.
But yeah, so I mean, there's something I didn't recognize that this particular wording meant CPAP, but I agree with you. I think it does. So yeah, if you were on a CPAP, better to tell them.
Yeah, and so like one of our standards we're working on, we're trying to help people understand like techno babble, right? Basically, for lack of a better word, how do we interpret this for the typical person so they can understand, right?
Right.
Yeah, and this is a prime candidate for some nice interpretation, don't you think?
Oh yeah. It'd be nice if there was a picture that said, "Oh yeah, I got one of those."
Yeah, or even if you can type in something that you have and then have it search and say, yes, it fits into this category. You know what I mean? Like, or Take
Yeah,
a picture
because
of the
I think how they do it is I think our company's assumption is if you don't know which of these ones to check off, you're going to check off this one and tell us what you think you have and go from there. But yeah, it'd be much better if people knew, oh yeah, I got this one.
Yeah, I mean, I don't know if a lot of people appreciate how vital CPAP is to a person's life. I mean, I think a lot of people think it's ordinary or typical, or a lot of people have it. And I think the fact that it's on this list gives a greater appreciation for these needs that people have, you know?
Yep. Oh yeah. And this is my last slide. So hopefully that gives you guys a feel of what you guys as a customer have to do, what we can do to help prioritize, for people with disabilities or people with certain needs. And also hopefully it informs, you guys on, the different aspects that we can do for, you know, within a utility and what we can tell you about what we know and what you have to tell us to help you.
Thank you so much, Larry, for this fabulous presentation, really thoughtful annotation of what's going on in the area and how you help people every single day. We really appreciate it. Do you have any suggestions about how we can raise awareness for people so that they can understand what they need to do to be safer in their home, or how they can make plans in case of an outage or emergency?
Well, I would say definitely the first thing you should do is, I mean, I'm showing you guys outage maps that my particular utility has. One of the things you should do is whichever utility each of you are in, is you should go and look on that utility's website. If your utility is big enough to have one, not all utilities have one, but if your utility has a website, go check, because chances are they have an outage map that can show you what they know about your system. And you should be able to just type in, all you got to do is type in, the name of your utility. If you're down and you're at PJM, you can type in PJM outage map and it should pop right up. And then from there, you can browse around and you'll find stuff. But when in doubt, call the customer service,
So
especially
one of the
when,
things we were talking about on our previous conversation was about cell towers, and when the cell towers lose power. And can you just describe for us, many of us are people in the communication arena also. And
yep,
so we know that even if there's an outage in an area, cell service may appear to be working well for a while, but
yeah.
limitations to that. And if you could help us understand that,
Yeah, so
great.
with cell towers and even telephone lines, so um regular wired telephone lines require power. So even though it's a nice myth that they say, oh, you lost power, but as long as you got a landline, it'll still work. But if you're on cable and that, it'll go dead because you don't have power. Well, that's true, sort of, kind of. And the way that works is there is UPS batteries at each of the telephone switching stations. And those batteries are designed to work for some amount of time, maybe 48 hours, 24 hours, 8 hours, depends on where they are. But what will happen is when those batteries start to get low, I have seen personally, go looking out on damage assessments, is they will bring little Honda generators and they will bring them out to telephone poles and they'll put the Honda generator there and they'll use it to power the telephone line. Now, is there enough Honda generators for every telephone line out there? Probably not. So there's probably some lines that will lose power for communications if the outage is long enough. And I worked a storm in 2008 that was an ice storm, and there was neighborhoods that I worked on that they were on day 11, day 13 with no power. And those generators, they didn't keep the phone lines worked great for the first day or two. By day 3, day 4, some people had communications and some people didn't. And it was just because of the reduced resources on keeping the telephone lines alive. Now, cell towers, what you'll find is, if the cell tower loses power, that cell tower may have a battery backup, but it will shut off. And you'll find that, yep, you got great cell service for about 8 hours after that initial de-energization of your town. But once those batteries go dead, now that it's not able to transmit and receive anymore. And maybe some of the towers have generators, but not necessarily all of them. So you will see reduced cell service. You'll see now, if there was 4 cell towers in an area, maybe 2 of them go offline if the power's gone long enough, which means the other 2 towers have to carry all the people's cell phones within the range, which may overload the network. So that's why you find that areas, they'll say, oh, the telephone networks are getting overloaded. It's because there just isn't enough power to support all of the towers. And not necessarily every tower is built with a backup power source.
Is there any way to know how many cell towers have backup? I mean, you when you drive around, you must see which ones have.
The way I would be able to tell, so that's the other thing is normally somebody like Verizon won't call National Grid and say, hey, my cell tower's without power. So they don't send guys like me to go check it. They'll just assume it'll come back at some point. That, like, Verizon doesn't call us and say, hey, something's wrong, come check it out. They've got a million customers that they're trying to go help with all the wires ripped off. So they figure it'll come back eventually. But the way you can tell is if you drive by it, if you're near the cell tower, drive by it and see if you hear a generator. If you can hear a generator running when the neighborhood's dead, it's probably got power and it's probably going to be fine. But if it's quiet, that means at best it's got a battery, and most battery systems are not designed to last more than a day, maybe 2 days at most.
So you and I were speaking at one point about what kind of alternative there might be to, like, use, let's say, satellite to look to see who has generators by figuring out during an outage who still has power or who still has.
Yeah. Oh, yeah. So the way we know who's running, so when we're in an area and we are worried, and this is the key, if we think the town is dead, it's bad if it's not dead, because that means a worker can't go and work on it. So it might be nice for you to know that your neighbor's got power, but depending on how that neighbor's connected that power, it's dangerous for the utility worker. So we actually go around trying to find this, and we do it one of 2 ways. One, we got the windows down and we're listening for generators. If we can hear it, we've got an idea who's probably making power themselves. And we always double check with them, how are you connecting that? We don't want you to backfeed into the system, because you might turn on your neighbor's lights, but you might also kill your neighbor. So we don't want that to happen.
And what about solar panels? How does that play into this?
So any solar or wind generation at a local person's house, based on IEEE 1547, must de-energize when the utility is offline. You have 2 seconds to turn off. From the point that the utility is off, they must turn off. And so that's an IEEE
solar. If you have your own solar panels, you have to turn off, even though you have solar panels, you have to turn off.
Yes, unless you go and make your own island. So now you disconnect yourself from the network, meaning you're no longer part of the utility. And now you have a battery backup system, maybe, or an inverter with those solar panels, and you've isolated. Now you are allowed to have your own power source.
So
but you cannot.
If you were providing help to under-resourced areas, people who have under-resourced power connectivity, but they have some power connectivity, and you were providing solar power for them, you would have to be aware of this. You'd have to make sure you could turn off when the local power utility is down.
And normally what they have is what they call a transfer scheme. So they have a system that monitors the health of the electric grid, and the electric grid says, yep, I'm running fine. So it's running fine. But then the electric grid disappears. So it sits there and it waits for those few seconds and says, okay, come back, electric grid, come back. Nope, you didn't come back. Okay, transfer. And now it isolates, and he opens up and he runs off it, but he's still listening to the utilities. So he can run all by himself for, maybe days, depending on how good that little island is. But once the utility comes back healthy for a couple of minutes, it'll say, hey, I don't got to generate anymore, and it'll click back in.
I see.
So that those kind of transfer schemes do exist, but they tend to be very costly. So this normally is not something somebody runs at their house. You know, the infrastructure needed to do that at a regular home is tens of thousands of dollars just to do the transfer capability in the battery system. I mean, and I'm thinking like 40, 50,000. So most people won't bother installing that. They'd rather install $20,000 and just have a solar panels, but that doesn't help you when you lose power. Oh, I see a question
I have a
from
question with
Ed.
Edward Friedman. Can
Yep.
you?
Yes, thanks for the great schematics of the infrastructure. Can you explain what happened with the deep freeze in Texas and how
Yeah.
that managed to take out such a large area?
Well, so that's an interesting one. That the one of the root causes I had heard was part of that Texas issue was actually the cooling systems down there. And what happened was a lot of Texas assumed the area would never freeze. So in the cooling systems, they never added glycol or antifreeze to their water cooling systems. So when the temperature got so cold, the cooling systems literally formed ice inside the water pipes because of how the systems works. And when the ice formed, it's in essence stopped the cooling. So the generators started to overheat. And to protect the generators from damage, they had to shut down. So that turned off a lot of the natural gas stuff down there was because it was kind of a cascade thing. You know, once one turns off, the other one has to work harder. Well, if it was just barely getting by because its cooling system was starting to freeze, but now it has to work even harder. Now it's overheating faster. It shuts off, and then it's a cascade effect. So that was one part of what happened down in Texas. The other parts is I heard there was some issues with some of the windmills spinning, though the windmills worked better than some of the other parts of the system, from what I had heard. But there was issues with like just multiple things go wrong. So and that's part of where that redundancy discussion comes in. Is by design we assume a lot of things you can have what they call an n-1. Any one thing can break, and the system should keep running fine. Well, and this is like inside that substation. So in that substation, any one thing can break. The whole transformer can break. The breaker can break. You know, any one of the, you know, maybe a control system for the breaker can break. And we assume any one of these things can break, and we got a plan to keep it running. But when you start having, well, this broke and that broke, and now this one over here also broke, the backup plans start falling apart. And if you have too many backup plans fall apart, the whole system collapses. And that's how you get blackouts. Whenever you hear about a blackout, it's when so many contingencies happened at once that we didn't have enough backup plans to cover them all. And that's when so like the last big blackout in our area up here in Northeast, that was the blackout of 2003. When that happened, it was because there was too many of my devices, the relays, that saw problems, and they were tripping on load. So in other words, there was nothing wrong in the system. It just saw too many customers pulling power through one wire, and it looked like too much current. Well, if that happens at one thing, then it turns off. But then the guy next to it sees even more current because his neighbor turned off. So he's got to carry more of it. And it's a cascade. One by one, they all started to see too much power, and the whole Northeast blacked out because everyone kept turning off when they weren't supposed to. And as a result of that, NERC, which is the North American it's one of the regulatory groups that in essence looks over the entire United States, and they are the body that works with FERC, which is the Federal Energy Regulation Commission. They in essence said, you need to come up with fixes to your design so that that blackout doesn't happen again. And so after the 2003 blackout, we redesigned and rethought of how to implement certain things to accommodate that scenario so that it would never happen again the same way. So whenever there's these big blackouts and these big things happen, we normally learn something and we completely change the way we're working. So like that Texas incident, I bet you it's a requirement now that almost all generators put glycol in their cooling systems,
Yeah,
just so that this doesn't happen again for the exact same reason. Something new can happen, but it won't be the same thing again.
right. So that sort of begs the question of how we mitigate risk. Um, and there's 2 points around that I'd like to make. The town of Concord, Massachusetts, has its own power company. I don't know how they generate it exactly, but almost all the wires are buried throughout the town. So it's not only is it much less unsightly, but they're not subject to weather events the same way. But a more serious threat than storms and wind damage, about 10 years ago, I had read that it was possible to take out one of these very large transformers with a high-powered rifle. If you can damage the steel enclosure enough so that the cooling oils leak out,
Yep.
it
Yep,
will
they'll turn it
overheat,
off.
and then you have a cascading set of failures. In fact, in the last year, there have been several incidents of that happening, both on the East
Oh,
Coast
yes.
and in the West. I understand that the way around this, to mitigate this, is build big thick concrete walls around the substation. However, there doesn't seem to be the legislative will to do that. Are
Well,
power companies lobbying for this? Because those transformers are the size of a school bus
oh yeah, yeah. The
and
big
take
the big
6 months
ones.
to build.
Oh, some of those big ones these days, 3 to 4 years.
Yeah.
So yes, the big ones that is something that we have done for risk mitigation. I have seen designs where they do the concrete. I've seen designs where the solution instead of that is just physically different locations of multiple systems. So, the loss of this one here, you'd have to go somewhere else to cause the loss of the other one. So they physically locate things differently. They make them out of different materials. We also change where we put our fencing so that you can't get close enough to need the barrier. So there is different aspects of mitigation for that scenario, because I've seen those kind of scenarios happen in our area in the central Massachusetts, and that there's been warnings of, hey, we heard this happen down in California, keep an eye out here, or down in the Carolinas. I remember there was a few incidents of some intentional vandalism to multiple stations, and they were worried that it was becoming rampant across the country, so there was warnings about that. So I mean, and some of these things, they're just in the news and you can see about it. But yeah, no, there's definitely different mitigations that can be done, and a lot of it actually is driven by regulation. So like the protection of that kind of scenarios are driven by different either physical security requirements or sometimes cybersecurity requirements, um, and there's regulators that are in essence lobbying for this to happen, and then make sure that the utilities enforce it.
So I
Yeah.
think another issue is like during that 2003 Northeastern fiasco, people were eating at the Chinese restaurant in our town and we had no water. People were bathing in the creek because, you couldn't get your wells to work. It was just a real, awful situation. People smelled everywhere you went, it was a very untidy situation. But I wondered if there are like people who do simulation to try to determine what kinds of scenarios would be risky and
Oh yeah, yep. No, we do run, and this is actually what they call our planning department, and they look 5 years, 10 years out, 20 years out into the electric system. So they predict what the loads might be, what the generation might be. So there's a lot of prediction and assumptions there. And they will run scenarios of, well, what happens if I lose this transmission? What happens if I lose this entire substation? What happens if I lose, Seabrook, one of the nuclear power plants? What happens if I lose, maybe a few towns that were interconnected? What if I lose any of these things? And we run all these scenarios, and they're prescription scenarios that
There
we
was
say,
there was a solar coronal mass ejection that took out most of Canada
Oh yeah, yep,
about
yeah.
15 or 20 years ago.
Yes, and in that scenario is a what they call ground potential rise, and what happens there is and they call it a ground a G, I forget what it is, G something, GMR, and what that is the magnetic pulse that comes from that coronal mass ejection causes a DC bias in the ground. So you raise the voltage in the earth. And when you raise the voltage in the earth, you can draw a current through the earth. And that current goes through all the grounded connections on all the transformers. And why that matters is as the ground current goes through the transformers, you start adding heat because it's I squared R. So the resistance of the transformer is constant. You've just added current, so I squared that, and you start creating all this noise and heat. AC transformers, which use the principle of induction and that from the changing magnetic waves, hate DC voltage, and that's what a mass coronal ejection causes is DC voltage. So it just cooks the transformers, literally melts parts of them. And once you damage the transformer, you're done. And here's the problem. Almost all of our system is a grounded system, so it's all connected to the earth. So if one of these events happen, you cook everything. And that's what happened up in Canada, is it just so happened that's where the current flow was happening, was up in Canada. And all those transformers got cooked because there was just too much current warming up all the neutrals in those transformers.
Mm-hmm.
Larry, this is Bob Pellegrino. So wouldn't you have relays to protect against that? The DC buildup?
To date, we do not have relays in there. I believe we have ways to detect it, but we are not currently tripping on that DC voltage bias. So that today there is not, and here's the worst part is that voltage thing is not something that happens quickly. It happens over the course of hours to days. So you end up not necessarily being able to say, well, I'll just look for a quick change. It's kind of more like a trend that happens. Some devices, and it's funny, this is back in the 30s and 40s, we used to add what they called Fenwal protection. And Fenwal was a temperature controller manufacturer. And the Fenwals would stick on the side of the transformer. And all they do is keep an eye on the temperature. And when the temperature went too high, we'd turn things off. And we did that to detect harmonics, but we stopped putting them in a lot of places because we came up with better ways to detect problems, like a change in gas pressure and a change in winding temperature. So we'd measure the actual winding pieces instead of just looking at the transformer as a whole. So we stopped putting those sensors in, and that might have been one of the sensors that could detect this. So we might have to go back to the old ways to mitigate this problem. But unfortunately, yeah, right. And even if you detect the problem, the only way you could stop it, so let's say you do detect that this voltage is happening, what you have to do is go and unplug the grounds from the earth of every transformer. These are solidly bonded and clipped, designed to handle hundreds or thousands of amps of current. I'm not sure how you go around disconnecting them. I mean, because normally you don't put breakers or some other device that can interrupt current. And that's the other thing. Most of our interrupting devices are designed to interrupt AC current, not DC. So it's like a whole new problem and process to do. And I feel as though when you say what would it cost to mitigate this, and then what's the likelihood of this event happening, you realize you don't want to pay the electric rates that are needed to mitigate this event.
But fortunately, we would see a coronal event happening hours or days ahead of time.
Yeah, speaking from the perspective of substations engineering, all of these things end up being a cost-benefit analysis, whether it's burying the distribution or transmission lines underground, which costs anywhere from 10 times to 50 times as much as doing them overhead, to protection of transformers with things like walls and so on, which is often almost impossible in existing substations because of other standards and requirements for clearances between equipment and, you know, the electric to ground distances and so on, or preparing for a mass coronal ejection, which happens relatively infrequently in terms of the severity that caused the Canada incident. All of these have a cost and has to be weighed against other costs and the likelihood of it happening, and what is required and what is just desired or would be nice.
Yeah, we'd love to build the Cadillac, but you don't want to pay for the Cadillac necessarily in your electric rates.
Right, it has to hit the rates then too, and the customers are paying for it.
Well, the other thing is it's challenging to figure out, to predict ahead of time what the real consequence will be, because you can't always know exactly where it's going to happen, and that's a moving problem, right, Larry?
Right, and that's, and you know, the blackout is a great example of that. You know, we didn't realize that the loading scenario could have caused that event. If we did, we would have prepared for it. We just didn't think that far down the what ifs path. And then once we figured out, wow, you know, this can happen, and it's risky when it happens, and it's bad when it happens. Now we spent big money to fix it. You know, we didn't just fix it in one little spot. We fixed it across the entire country.
So
So
one thing that might be possible is your 3 through 5 items on your list. Frank has a question. I think he was raising his hand. Frank, were you raising your hand? Is that right?
Yeah. Can
Yeah.
I
Sure.
ask a question now?
Yes.
Yeah.
Oh yeah. Well, Larry, thank you for the talk. Very, very nice talk. And about 2 weeks ago, I read a paper in IEEE Transactions on smart grid. Okay. And they use AI techniques to try to identify the appliances, and they use a non-invasive means or technology to do that. So I'm wondering, in the practical environment there, what you're talking about today, for instance, you have a critical customers and a critical the equipment or devices there. And if anything goes wrong, is there any way not to break into the house and see what kind of equipment is that, what kind of device is that? Is there any way, how do we do that practically?
So to have that better visibility, so there is a program that we're doing within our company called AMI, and that program is Advanced Metering Intelligence, I believe is what the I stands for, or integration. I forget. But in that scenario there, they're building out a network of all the devices across every connection to your house. And then they'll use AI to do prediction stuff with it. So we'll in essence know, is your meter spinning? Is your neighbor's meter spinning? And we can take out of the equation you calling me to guess it. And we are getting there. I think, at least in my company, we're probably 3 to 5 years away from that capability.
Yeah.
But when that hits, that's where the AI will kick in with, wow, you know, what if I knew this and this and this were happening? I could predict stuff. And then now I can tell the control center predictively, you know what, this is probably something bad. We should probably open this device over here so it doesn't get worse. And I think we are going in that direction. But I mean, most of it is we need the data. Once we have the data in hand, then we can play with the analytics on it. And I mean, and that's what you find now is, you know, most of our analytics are based on reactive data, not necessarily.
Yeah, I mean, like I was asking before about the 3 through 5 items on your list of like prioritized customers, for example, right? So if someone modeled what happens if if you use different modeling strategies to model what happens if different clients lose their connectivity, because I mean, maybe people live in rural areas because they can't afford to live in a central area, but they're prioritized differently, but they may have much more significant needs than people in a more suburban region, or people who use more power. Like, I mean, when you hear about the things going on in Atlanta, for example, where they have like the whole state of Georgia has a significant private ownership of the electric grid, and they prioritize business clients or more, wealthy neighborhoods, people in a certain zip code, for example. And so people in another zip code may be targeted for brownouts during peak periods, and those people may be suffering because perhaps, as Frank was saying, their appliances may not be getting the level of power they need to run optimally. And perhaps those appliances may eventually not really work well enough for them to have their insulin secure.
Yeah, so with regards to how they do the prioritizing now, so for example, in the event there is too much load and not enough generation, there are systems in place to protect the grid from collapsing so you don't have a blackout. One of those systems is what they call the under frequency system. And what it does is it looks at the whole system, because everything should run at 60 hertz. And if it starts to drop below 60 hertz, that means the customers want more power than the system can provide. So the system starts slowing down. So what we do to keep the system stable is we kick customers off. Now, how do we pick which customers to kick off? We actually don't look at their meters or any of that. It's based purely on where do we have devices that we can turn things on and off, and where are the choke points in the electric grid. So for example, if there is a lot of customers here and there's a few customers there, we're not turning off the few customers because we're trying to keep the large amount of customers on. It's probably going to be the other way around. We're going to turn off the large group of customers because we need to drop enough load to keep everybody else running. Now, if we only need to drop a little bit of load, maybe that area that only has a little bit of load is where we need to drop. And in this under frequency scenario, what they do is they do what they call staged connection drops. So there's the stage one. All right, we're starting to drop frequency. Let's kick off a few customers, and we're gonna do a little bit here, a little bit there. It's gonna be all around the system because we got to drop it equally, or the generation won't help. But then, nope, that wasn't enough. We got to go to the next tier, and we just keep picking and it's not random. They're picked based on where the load, where's the generation, and where does the power need to go? Because the goal is to keep
predictable load, though. Like, I mean, do you have the same load over and over again? And do
yes.
Okay, so you know which neighborhoods are experiencing these things, and that's really the question I have. What are the profiles of those neighborhoods?
So we know what the profiles are power-wise. We don't take into account any other aspects of it. It's purely based on the electrical attributes. We don't go and look and say, now, that being said, if we're going to turn off power, we're not going to turn off a hospital that's going to kill people. So we will intentionally say, what can I do to leave that hospital connected? You know what? I got to turn off some individual customers. Now, if that customer is registered with us as a critical customer and there's enough of them on a feeder, maybe that feeder isn't the first one we go turn off. But at a certain point, we got to kick off enough customers. There's going to be collateral, especially when the decision is, do I kick off 5 critical customers or do I kick off a hospital? I'm going to save the hospital.
So it seems like there's an opportunity here for us to look into those situations and see.
Right. And I mean, and that's
affected,
Yeah. And I mean, a lot of that is prescribed by the regulators. I know,
I think we have an opportunity as IEEE members who go to Washington and talk to Congress to, to appeal the case for people who might be affected unevenly, for example.
Right.
But we don't know. Yeah.
Oh yeah. No, and I mean, and in the example that I'm giving with the under frequency, it's never operated, as far as I know, in New England. Or well, it hasn't operated since the blackouts. The blackouts, I think, were the last time the under frequency stuff happened. So when you say, oh, we're worried about the rolling brownouts, those don't happen in New England right now. Now, I know in California, they do the rolling brownouts. But again, what are they doing? They're trying to get rid of load because they only have so much generation. And they're looking at it as, I got to open a breaker. So I've got to turn off so many customers. And I think I would hope what they're doing is they're rotating around. So they say, well, if I got to do it 10 times, I'm going to keep picking different areas until I've done all 10 times. But that might be a little bit more political because that's not an automated system. Whereas like the under frequency stuff, that's very automated. We plan ahead, we pick where we need to, and it happens all by itself. There's no human deciding these things. The human part, when you're saying, well, they turned off this neighborhood, that might be based on the need.
The other human part is how many people in the neighborhoods who have needs know they should get that form and fill it out and send it in,
That's probably the most critical thing. And I think that's the key is I don't think there's a lot of awareness of, to protect, if you are a critical customer, there are tools out there to protect you, just like, if you are a person that is financially having a hardship, there are tools at most utilities to deal with your hardship. Now, the answer isn't going to be, we're going to give you power for free, but the answer might be, we're going to subsidize you. We're going to work within your budget. We're going to change our billing method so that it is easier for you. Or we're going to point you to somewhere that, hey, there is free money for you to have if you go fill out these forms. Those things have existed for a long time. A lot of people went and found those things in the last 2 years when we had the big natural gas crisis. When the natural gas prices skyrocketed, my utility specifically did outreach to the community and said, come and talk to us in person, come into a building and talk with us. Tell us what your situation is and we'll tell you what services you qualify for. And they aren't new services, they were always there, but maybe you just didn't know that they were there for you.
So as IEEE humanitarian people who are running site groups and reaching out to the community, we can play a big role in spreading this information, finding ways to let the community know that these things are available, interpreting those forms so
Yes.
that people know who qualifies in an effective way, in a way that
Right.
makes a difference in people's lives. Edward,
Right.
do you have a question?
Yes, and thanks again for a great presentation. A friend of mine's wife needs pretty much round-the-clock electrical power for respiratory issues. And so what he has done is get one of these, I don't know if it's a Generac or a Kohler, big, it's about 6 or 7 feet long, runs on natural gas, and so
Emergency
it will
backup power.
automatically cut in and start generating. He did this about 10 years ago. I think he spent about 20,000 on it. What do you think of the robustness? Because that depends on the natural gas supply too. The robustness of that versus some of these new systems Tesla and Generac are selling that are battery based.
So the biggest difference between the battery based systems and the generator based systems is duration. The battery systems are very reliable, very fast. They work instantaneously. You won't even notice that they switched. The downside is most battery systems, a Tesla battery system might be, I forgot how many kilowatt hours one of those is. I want to say they come in like 2 kilowatt hour modules. So if you think of, my house, for example, and I have little data things because I like to keep track of it. My house runs around 1,000 watts constantly. And sometimes I go to 2,000 to 6,000 watts, but base load is about 1,000 watts. That means one of those Tesla power walls is only going to give me power for 2 hours. And that's great if I'm just trying to ride through that 15-minute switching or little brownouts I'm trying to ride through. But if I have that 11-day outage, I'm in trouble. That Tesla wall isn't going to help me. Now the generator, whether it's a gas generator, natural gas, my neighbor actually right next door, she elderly lady, and she has a Generac generator, and she runs it on propane. And that propane is good for about 3 to 5 days of continuous nonstop running. And the mindset being within 5 days, she can get her propane company to come on site and deliver another full tank of propane
Right.
before, she runs out of electricity, so that she always has it. That's part of that risk stuff. The natural gas system, it runs great until it doesn't. Up in Massachusetts, up in the area where we had the big gas explosions. Those people that were relying on gas ran out of gas for a couple of weeks while they repaired the gas system. Now, what's the likelihood that the gas system and the electric system have a problem? It's probably not great that both of them will go down, but it is possible. The battery system mitigates that, but only for a very short window of time. And I mean, to give you an idea, I've stayed at a bed and breakfast that they live 100% off grid. They don't even have a connection to the utility. They have a solar panels to cover their power for the day, and they run batteries at night. They have a huge battery system for their house, and that battery system costs them around $20,000 just for the batteries. And the batteries are only good 5 to 10 years, and they run only 8 hours. That's all they can do.
I heard these
So
Generacs only are supposed to be 5 to 7 years anyway, right? I think the Generacs don't really warranty their equipment much longer than that, right?
yeah, warranty wise, I would agree, but I mean, most of these things are they're little small engines. Most of them, even though, for example, your lawnmower might only have a warranty for 3 to 5 years, there's plenty of guys that have a lawnmower that are 20 plus years old. I would say there's a lot of these generators that, if you do the proper maintenance, do the oil changes when you need to, change the spark plugs, you do the normal maintenance on them, change the starter battery, you'll get 20, 30 years out of some of these generators, because I mean, they're no different than any other small engine you might have for most of them.
Well, that's really great to know. I wanted to offer the opportunity to invite Larry back for another talk in the future on a topic that it seems like this is a very interesting topic to everyone, and perhaps he could go into another aspect of this topic on a future talk. Would people be interested in that?
Yeah. Could I ask another question? So you brought up shutting down neighborhoods. And when you talk about something like that, it really depends on the system, the utility, okay? Because I don't know how National Grid has up in Larry's neck of the woods, how their distribution system is arranged, but the Con Edison system has networks. Back in
Yes, that's a good point.
1990,
Very different.
we lost Seaport Substation back in 1990, which shut down the Seaport network. All right. The rest of Manhattan was still running. The Seaport network was down. We ended up running cables, picture huge extension cords on the street. We ran cables on the ground against the curb to pick up the network. There was this hospital that went down. We provided a generator. Actually, there were a couple of hospitals. There was a nursing home. So we being Con Edison, brought generators to supply those customers until the network could get back up. And within 8 days, we had 2 of the transformers in that substation back and running. Okay, so it really depends on your system. When you talk about shutting down a neighborhood, we're not shutting down neighborhoods because of the people that live there. They're shut down because the substation blew up or burnt down, and that whole network, that whole neighborhood or network is down. But again, utility does whatever it can to get those customers back ASAP. So within 8 days, we had the customers restored.
Yes. No, and that is a good point, Bob. And all the stuff I am talking about tends to be the types of designs that we do in a suburban or we do in a rural area. And most of my substation design example that I put on the screen, it tends to be a suburban or a rural. What Bob's talking about, the network system, much higher reliability, but when it goes down, it goes down hard, and it takes a lot more effort to get it back because there's so much reliability built into the network, and these networks tend to be very urban, very population dense. All the cities, in my area, Providence, Worcester, I'm assuming Boston has it. That's a different company than than I currently work for. But Syracuse, Rochester, those all have network systems, and the way those
And
work
then
is
the
lots
other
of
thing
feeds.
was the transformers. You mentioned, someone mentioned shooting a transformer, putting a hole through the shell of the transformer. So a lot of our transformers, especially in the city, are within an enclosure. The actual transformer is inside a steel enclosure. So the issue is not going to be firing through the outside and hitting the transformer. It's actually, you're talking about hitting the porcelain insulators. If they can get to the porcelain insulators, then you got an issue.
Yeah.
Yeah, I think what you're saying, Bob, is that each of the grids has its own design and issues and strategies and risks. And
Correct.
and also like geography does play a role, so depending on where you are in the United States, you may be covered by a different utility or regulation.
Different designs, regulations.
Right. There's definitely different designs.
Yeah, so in some parts of the United States, there are still, choices that utilities can make that may seem ordinary to us as engineers. Oh, yeah, of course, we're going to save the majority of the clients as opposed to the minority of the clients. But that may wind up being an unbalanced kind of unfair disadvantage to some people.
Yeah, so like, for example, in Manhattan, we're designed for N-2. So we literally can lose 2 feeders, 2 transformers, 2 breakers before things get hairy. Okay. Outside of the city, it's N-1, as Larry mentioned. So outside of the congested area of Manhattan and the Brooklyn, the Bronx, Queens, so on and so forth, Staten Island, outside that area, you're N-1. So they can only stand losing 1 piece of equipment or 1 feeder, and then it doesn't really matter, because no matter what happens, the way Con Edison works is if they lose 1 feeder, no matter where it is, the operations department is geared up to get that feeder back in service.
Oh yeah. There is no outage that we sit around and do nothing. It's just a matter of how quickly and how many people we have to fix it.
Correct.
Yeah, having grown up in New York City, before moving upstate to the place where you have to bathe in the creek when you have no power, it's a tough act to follow, Bob. What goes on in New York is really wonderful. So I'm grateful that you guys do such wonderful work in New York. Important, right? What you guys do. It's very important. I wanted to let you know that we have some very interesting upcoming presentations. Tom Willis is with us tonight, and he's going to be speaking about electromagnetic compatibility in the near future. In addition, one of his colleagues, Dr. Shaki Johnson, is going to be speaking about the Shares Network. Tom, do you have a moment to explain what the Shares Network is? Tom, are you there?
He's on mute.
Aha, he's on mute. Okay. So the Shares Network, has everyone here heard of the Shares Network?
You saying shared?
Shares, SHARES. It's the Shared Resources High Frequency Radio program that provides an additional means for users with a national security and emergency preparedness mission to communicate when landline and cellular communications are unavailable. So one of Tom's colleagues, Shaki Johnson, who we've met on previous meetings, will spend one of these sessions describing how the Shares Network works to deal with emergencies when communication lines go down. So that's another one in this series, and I hope you folks will be joining us. And Tom, are you there? It looks like you're on mute, right?
Yeah, I finally found the mute button.
Yeah, the Shares Network, it's a HF radio network. It's a joint federal government and commercial network. And I mean, at AT&T, it is the network of last resort. If something truly terrible should happen in the phone network and you say lost all communications between, say, Philadelphia and New York, it would be really handy if you were working in the central office in New York, if you could actually talk to someone in Philadelphia to try to get things back up and running. And if that happened, you would, you could use this HF radio network to actually have technicians talk to each other between the central offices. The last time this network was actually used in, a real scenario other than just, tests, was during the 9/11 attacks on the World Trade Center. So the network did go into operation there, trying to get New York City back up and running. So yeah, it's kind of an interesting network, and Shaki, I'm sure, will tell us all about it.
And then Tom will be spending some time telling us about electromagnetic compatibility. Tom, you want to spend a couple seconds reviewing your talk? Well,
I haven't written the talk yet, but the basic concept, I'm sure everyone is familiar with. All electronic devices will emit electromagnetic radiation. Radio waves are there during their normal operations. And if you get a lot of these devices close to each other, they can, in certain unfortunate scenarios, have negative effects of interfering with each other and then disrupting their operation. So, that's obviously a very important topic for folks that build lots of equipment that go into small areas, and certainly in the telecom space, that you've got to worry about that for equipment that gets all loaded up into a central office, to make sure that that equipment is not going to have bad interactions with each other when you get it all in the small rack and turned on. Other medical devices, it's another thing to be concerned about, because I'm sure folks may remember when pacemakers came out, people were warned not to go near microwave ovens with their pacemaker, and that was an electromagnetic compatibility issue. So those are some of the issues that have to be considered. Back to you, Kate.
Thank you so much. And then the next speaker we're going to have next month will be Amanda D.L. Dillon, who has a standard on user interface for the blind. So I welcome you to join us at any time. And if anyone has a final question for Larry or a comment or compliment, we're willing to hear. Victor, do you have something you want to say? You're unmuting.
Well, I just want to say that, Larry, this is a very insightful talk.
Oh, you're welcome.
No,
was
I
fun.
don't have anything to say, Kate, except that this is an excellent talk indeed. My only thing I'm asking is, how does the future hold when we will not rely less on the grid, but we will have our own energy generated through solar and hydrogen and other things, as opposed to what you talked about? How do you see that too? And is it more reliable to rely on your own internal generated?
Well, I would say I have now seen more customers do it, and the reason that they choose to do it is one, for that independence of the system, but the other one, it's a lot of times nowadays it's come down to cost. That bed and breakfast that is near me, they didn't connect to the utility, not because they didn't want to, but because their house was far enough back from the road that it was cheaper to install solar and be independent and look at that than it was to pay to have the transmission and power lines connect to their house. It was going to cost so much to get the infrastructure out to them. It was cheaper to not do it. So that tells you just how cheap it's getting to do it yourself. So I see the world where people are going to make it.
Or even if you use the grid, and you have this backup, there is no problem when you have a failure.
Right. Yeah, I see us. I think that's going to be the biggest transition first. Is people are going to start putting more Tesla power walls to take a little bit of the load. They're going to be putting in that generator so that they can isolate because it's so critical for them. So I think that's going to be the first step you're going to see a lot of. And I mean, part of the advantage is if we can start making power ourselves in a more localized fashion, the grid doesn't have to be able to handle as much power flow, which means in time, we won't have to build it to carry everything. We can build it to only carry the emergencies, the backup plans. And if you get to the point that you only have to build that, now the costs come down because now you're not building it to carry everything. You're only building it to carry some things.
Like microgrids, for
But
example.
again, that applies to rural areas.
Right.
You're not going to do that for a Manhattan or a Bronx
and
or
that's a
Brooklyn
good
or
point.
Queens. We have high dense slopes and buildings like right on top of each other.
Exactly. And that's the key is if you can't generate the power in the footprint that you need, then the grid isn't going to go away in that scenario.
Right.
And New York is the example. The need of power in that area surpasses any capability to generate in that area. I mean, even if you started building nuclear power plants all around Manhattan, you probably couldn't make enough. And not that anyone would want to live there in that scenario, but you know, as an example.
Well, to give you an example, so when Con Ed went to well, not Con Ed, but utilities went deregulated a number of years ago, way back when, where they had to sell their generation. Con Edison did not sell their generation in Manhattan because you need generation close to the load. There's so much load density in Manhattan, Brooklyn, Queens, the Bronx. You need in-city generation to pick up that load. So we
And it was
kept
too
our
risky,
gen
right? I mean,
stations in Manhattan.
yeah. And then in those scenarios, Bob, right? They needed to keep it just for the security to ensure they could power the city. You know, they didn't
Exactly.
want to risk it going to a third party.
Right. Well, you need the generation close to that heavy load, that big load.
Yep.
Great job, Larry. Awesome presentation.
Oh, thank you. No, it was fun to go through this with you guys.
It's fun to see everybody here tonight too. And I just want to say thank you again. And this recording will be made available as soon as possible. Thank you.
All right, great. Thank you.
Okay, thank
Thanks,
you.
Kit.
You're welcome. Good night.
Good night.